Welcome to Homework Lib.
As is the case with a lot of these problems, this particular question revolves around uh, figuring out wavelengths of light for semiconductor devices. So it's mentioned in the problem that we have a very pure germanium sample, and we are going to basically be examining when we excite electrons from the valence band up into the conduction band, making a particle-hole pair. Now, for uh, this particular system, apparently it requires 0.67 electron volts of energy to create that pair. So, this limits the maximum wavelength that we are able to observe using the system. Anything that is a higher wavelength will be too low of energy to be observed because it won't create the pair. So by going back to our often used equation for the wavelength of light being defined by the Planck's constant times the speed of light over the energy, or conversely, you can write it as the energy is just like this. We are going to be using this first form because we're given an energy and the wavelength for Hc all on 0.67 eV is 1.85 micrometers, or 1,850 nanometers. And also in the question it asks, in what portion of the spectrum does this lie? Well, this is pretty long. This is a pretty long wavelength. So this is squarely in the deep infrared part of the spectrum. However, for the part B of this question, it asks us to consider the same exact thing except for silicon, which has slightly larger band gap, so the electron has to go further. And this energy is 1.12 electron volts per pair. And using the same exact procedure that we used for this stuff, we can get an expression for our wavelength. That's Hc over 1.12 electron volts, which when you do the math, you get 1.11 micrometers, or 1,100 nanometers or so. Now, this is still in the infrared regime. However, it's much closer to visible light than the germanium result. So you are only about a few hundred nanometers away from being in the visible light regime. So if you want to view more infrared light, then germanium is probably the preferred material to use here.